A reminder that quiz 2 is Tuesday. It will be in your recitation or discussion sections, your Tuesday discussion section, just like last time. And quiz 2 will cover all of chapter 18. I will finish up chapter 18 today and start with chapter 19. So I was thinking about this business just for an introductory comment. You know, I'm filming my lectures and we're putting them up on a YouTube channel. And people are actually watching them. We're getting, 40, 50 views per video. What do you want, 10,000 views? What do you want, you know? So, but I think I've noticed that you all aren't coming to my class as much. So this is sort of like, I've never done this before. I've never filmed myself and put my lectures up. And I'm glad I did because I think it'd be good. I think it's good to see what I do. I'm sure that at some point someone will pull a piece out of that and prosecute me for some criminal activity, or you know, maybe they're good and I'll have to audition for a job someday as a teacher and I'll be able to pull these videos out. But so I'm glad I did it, but I don't think I'm going to do it again because I'd much rather you come to my class than sit and watch me, a virtual me as I have a poet friend who calls all things, you know, like your cell phone screen and your laptop screen, he calls that the greasy rectangle. So I'd much rather see you see me live than see me through a greasy rectangle. So anyway, lesson learned. All right. So I'm going to finish up. So it's the last bit of, not the last bit, but the last bit of this chapter on acid-base chemistry. And last time we were talking about salts. And I tried to break them up into two classes for you, organic salts and inorganic salts. And I made the point that organic salts often, the anion, for example, might be a base, or the cation might be an acid. And so the point of saying that is that quite often, an organic salt, you throw it in the water, and we gave the example, let's take, for example, there's a fun molecule, it's called aniline. Do I have this right? Let's do this molecule. And of course, this is a base. Whoa! I can make the hydrochloride by reacting with HCl. What do I get? The hydrochloride is a salt. Now, but it's an organic salt. It's got an ordinary inorganic anion, but it's got this ammonium cation. Now, you throw that into solution, and so if you take that salt, which is a hydrochloride, right? Better know what a hydrochloride is. We're going to call it NH4 plus chloride. Throw it in the water. You get, NH3 plus, you get that, plus that. So now you very clearly see that is a salt because another name for a salt is an electrolyte, and that is a substance that releases ions into a solution. Boom, there you go. But you know that is a weak acid. Or you better know that for quiz 2. So you know that can give you back the amine plus hydronium ion. So again, it's a salt that when you throw it into water, makes the solution acidic. And there are salts when you throw them into water that make the solution basic. Now, and that's almost always the case for organic salts. So it'll be one way or another, acidic or basic. Now, inorganic salts, there's bunches. There's bunches of salts that are neither NiETH acidic nor basic when you throw them in the water. All of these salts that we're so familiar with now, potassium nitrate, sodium nitrate, magnesium chloride, the anions have no basicity, the cations have no acidity, so you throw them in the water, they don't change the pH any. And so the common inorganic salts, garden variety inorganic salts, don't do that. But, on the other hand, there are clever salts that are able to change the pH of the solution. There are salts that are basic. How do you make a salt basic? Well, let's say we have sodium fluoride. So, solid, it's a salt. It did its salt thing, it released ions into the solution, but you know, or you should know, that fluoride is a weak base. So once that fluoride hits the solution, so there are clever salts, and the way to identify one of these clever salts is to look at the anion. Is the anion completely non-basic like chloride? Or is the anion a base like fluoride? And if the anion is a base like fluoride, then it's going to make the solution basic. And then there are salts that make solutions acidic. Lots of examples of those. So for example, ammonium chloride is a salt. Throw it in the water. It gives you the ammonium ion and the chloride ion. So the salt did its salt thing. It released ions into the solution. But you know, or you better know, that ammonium is a weak acid. It's the conjugate acid of the base ammonia. So ammonium is a weak acid because it's the conjugate acid of the base ammonia. And so there's a clever salt that makes the solution acidic. So, some salts, you throw them in the water, they don't change the pH. Some more clever salts, you throw them in the water, they make a solution basic. Some clever salts, you throw them in the water, they make the solution acidic. But how do you identify these clever salts? Again, look at the anion. Is it a base? Well, then the solution is going to be basic. Look at the cation. So you look at this one. Chloride, is it a base? No. Look at the cation. Ammonium, is it an acid? Yes. It's going to make the solution acidic. So study the anion, study the cation, and ask yourself, are these things acids or bases? That's how you figure it out. Now, there's another fun chemistry, one that I really like, and that is multivalent cations in solution. So let's take iron 3 plus, aqueous. So we know, we established, over a month ago, that iron ion is not naked in the solution. That water molecules, again, we go back to one of the Colonel's favorite sayings. You can understand a whole bunch of science, physics, chemistry by considering simple electrostatic arguments. You've heard me say this now about 5 times, but we know that in water that thing can't be naked because the water molecule, as we talked earlier, has a dipole. It has we draw that with an arrow like that. That end has a partial positive charge. That end has a partial negative charge. So simple electrostatic arguments say that the negative end of that molecule, water molecule, is going to be very highly attracted to that high 3 plus ion. Here's the way to think about it. There are lots of examples of monovalent cations. Indeed, all of these ions lots of examples of monovalent cations. Indeed, those are the divalents. Monovalents in group 1A, lots of examples of those. Divalents, no. I tried. Divalents in group 1B. Trivalents are more rare. There are some, of course, iron and ruthenium, but they're more rare. Tetravalent ions in aqueous solution, exceedingly rare. And so what is it about these high valent ions? Well, the problem is that makes an enormous electrostatic attraction between these two. So here's the way to think about that. So I'm going to just draw. Usually we say this thing called the coordination number. That comes up in the next chapter. It's the maximum, in this example, it's the maximum number of water molecules that you can put around an iron 3, the maximum number. And that's called the coordination number. Again, we will hit this in a big way in the next chapter. It's the maximum number of water molecules in this example, and for iron that turns out to be 6. So again, a reflection of that iron not being naked, it's actually coated. It has a water jacket on it. Very handsomely attired in its 6 water molecule jacket. Now, I'm going to do a little bit of sleight of hand here. I'm going to pick on one of those water molecules. So there's 5. And then I'm going to pick on this one water molecule right here. And this whole thing is 3 plus, and it's in water. So this 3 plus, as I said, many examples of monovalent cations, many examples of divalent cations. There's certainly examples of trivalent, but they're fewer. And that's because this electrostatic attraction is so strong. There's that pair of electrons being donated into that iron. It's so strong that it essentially becomes a bond and kicks that proton off. So you get that. All right, let me do it this way. So what happens is a pair of electrons comes in here and forms a bond with that guy. We might draw it this way. So in doing this little trick,
Is that supposed to be a D sign or is it a plus sign?
where's a plus sign or minus sign?
Right there.
Oh, I'm sorry. Thank you. Yes, that's a yield. So again, what I'm trying to show you is, and the sort of overriding issue is that high valent ions aren't stable in water. If water has the opportunity to do something with a high valent ion, it will. High valent ions are not stable in water. If water has the opportunity to do something with a high valent ion, it will. What can it do to that high valent ion? Well, it's going to take one of these water molecules and form a bond with it and spit off a proton. And now it's effectively a 2+ ion. You see what water's trying to do? Doesn't like that high valent ion. That high valent ion, that valency is so hard it can just rip those electrons out of that water molecule, giving you this OH iron bond and effectively making the charge 2+. So by this route, water makes a more stable chemical species. So you might think about this iron 3+ being a reactive chemical species in water. Does this reaction to get rid of it, to get rid of the 2+, get rid of the 3+. So again, high valent metal ions not real stable in water because of this kind of chemistry. It's basically it's forcing a water molecule to lose a proton. Okay, now this is very common in trivalent metal ions. So cerium 3+ will do this. Ruthenium 3+ will do this. To some extent, divalents do this, but to a much less extent. So for me, the way I remember this is that divalents don't do this at all. But that's not rigorously true. Some divalents do. But the big issue is trivalents and higher in solution do this kind of chemistry. And got a humorous anecdote from the laboratory. This is when I was working at Colorado State University. I used to work at Colorado State. I've worked a lot of places. You know, one step ahead of the law every time I moved. Worked at Colorado State University. And one of my PhD students was making solutions of iron 3, and we were using them to make a polymer, very interesting polymer, a polymer that conducts electricity called polypyrrole. So he comes to me, so we make these, we were making like 1 molar iron chloride solutions. And he comes to me one day and he says, I had to throw all the iron chloride out. I said, what? He says, yeah, it was bad. I said, what do you mean it was bad? He says, well, I made a solution of it and measured the pH, and the pH was 1. Something, contamination of that iron 3. He didn't know this chemistry. He didn't know that trivalents was unstable in water and will kick off a proton and make the solution acidic. And indeed, the Ka here for iron So again, now I've got you calibrated about what the values of Kas for acids. Garden variety Ka, 10 to minus 5. So as weak acids go, this is getting on the strong side of a weak acid. And so at 1 molar, you can do the calculation. You find out that the pH is close to 1. So lots of interesting salts can do interesting things. But in this subject, and again, for my reckoning, trivalents do this. Some divalents do, but to a much less extent. So things like this. There is this ion cerium 4+. It's the one example I know of a 4+ ion that can be put in water without exploding or something. But of course, it would most definitely do this chemistry because it has a 4+ charge. All right, so we got all this business about salts, and they can be acidic, they can be basic, etc., etc., etc. All right, one more topic from chapter, this is 18, yes? So we've had various definitions of acids and bases. Arrhenius had a definition. We had our pal Arrhenius. And of course, the most useful one perhaps is the Bronsted, Lowry. This is perhaps the most useful definition for acids and bases. But I want to lay a new one on you, and that is Lewis acids and bases. So the final topic in chapter 18, Lewis acids and bases. This guy Lewis, this is the same Lewis of Lewis dot structure fame. He was an early 20th century American chemist at Berkeley. And a lot of people thought he should have won a Nobel Prize, but he never did. And I think he didn't win a Nobel Prize because what he did was to make freshman level generalizations that really helped students, like Lewis dot structures. And that became widely accepted, and it became sort of the dominant way of thinking about organic molecules and other substances. But I think the Nobel people thought it wasn't, heavyweight enough, not deep enough, not, going to cure cancer or anything like that. So, in my opinion, he should have won a Nobel Prize, but he didn't. You can't win a Nobel Prize if you're dead, by the way. And I always like to say this about my scientific career. I'm one experiment away from winning a Nobel Prize. That's correct. I'm one experiment away from winning a Nobel Prize. I just don't know what that experiment is. All right, Lewis acids. Now, Lewis acids and bases. Let's consider base first. I've drawn our friend ammonia so many times because it's such a simple prototypical base. And from the day one when I drew this chemical on the board, I said its real defining feature is that lone pair of electrons. And it's that lone pair of electrons that makes it a base. That lone pair of electrons makes it a base. And we say, well, yeah, you can throw in HCl, and boom. From the Bronsted point of view, that base is a proton acceptor. Right? That's your Bronsted definition to make the salt, which you now know is an acidic salt. So again, Bronsted said the base is a proton acceptor. There it is. Lewis simply turns it around and says, no, the base is an electron pair donor. That's what Lewis does. So that then allows us, so again, for me, whenever I think about Lewis acids and bases, I begin with base. because it's easy for me to remember that base is about a pair of electrons. And so that allows me then to remember that a Lewis base is an electron pair donor. So there's your definition, which you will have to know. A Lewis base OR, donor, yeah? Not ER. So a Lewis base is an electron pair donor. So Lewis just turns the definition around. Bronsted says a base is a proton acceptor. Lewis says, no, let's not think about it that way. Let's think about this thing donating a pair of electrons. And correspondingly, a Lewis acid is an electron pair acceptor. So those are your Lewis acids and bases. So now, quite frankly, in most cases, it's easier to think Bronsted than Lewis. But there are some weird examples of molecules that you might categorize as acid-base chemistry where only the Lewis definition works. So for example, the molecule that they always drag out when they want to illustrate a Lewis acid, what are the chances I could hit boron? The molecule you always drag out is some sort of boron molecule. X might be chloride, X might be fluoride, X could even be OH. But boron has this feature that it forms 3 bonds. There it is up there, group 3A. What are the chances I can hit boron? Used to be it was a lot bigger, and I was so much better at it, and it's not, they made it small now, and I can't hit it now. Boron, there it is. Are you ready? Not even close. It's just freaking pathetic. What the heck, what happened to me? Must be the age. Clearly, I overcompensated, but you can see I was in the right direction. All right, I give up. You know where boron is, right at top of 3A. So boron forms these compounds with many, many, many different substances. And they have this characteristic feature. They have an unfilled orbital. And so these things are Lewis acids. And they can react with a base, like our friend ammonia. And the Lewis base can do its Lewis base thing, donate a pair of electrons. The Lewis acid can do its Lewis acid thing, and it makes this thing called an adduct. I'm going to just draw the X's out. Whatever these X's are, fluoride, hydroxide, whatever. And it makes that molecule. So that molecule is sort of your quintessential example of Lewis acid-base chemistry. You've got this molecule, this boron-containing molecule. It's electron deficient. It has an unfilled orbital. It says, I need electrons. I like electrons. I want electrons. I desire electrons. Give me electrons. That's what a Lewis acid says. A Lewis base, for me, is easier to think about because it's all about the lone pair, whether it's Bronsted or Lewis. So it's the Lewis base. And bingo, bango, bongo, it donates its pair of electrons, and there they are. We now draw it as a bond. But that's that same pair of electrons that are now shared between the molecule. So Lewis acid-base chemistry also can be thought of. So here's an important acid-base reaction, which I think we can also call Lewis acid-base chemistry. So I mentioned to you, we have these water purification system up in the lab. If you do chemistry, you got to have really clean water. Can't be tap water or anything like that. So they distill the water, and then we run it through our super duper water purification system. Takes everything out. But if you take that water fresh out of our water purification system and measure its pH, you'll measure a pH around 6. It's like, what did I pay these $20,000 to, for a super duper water purification system? Well, clearly my water must be contaminated, right? Because it ought to have a pH of 7, because that's the pH of ultra pure water at 25 degrees C. Why does it have a pH of roughly 6? The answer is there's CO2 in the air. And that CO2 gas immediately reacts to make carbonic acid. And so within minutes, your ultra pure water has carbonic acid in it. Now, you can get rid of it easily. You just boil the water. And that reaction will go right back, and bingo, bango, bongo. And it's acidic, of course, because carbonic acid in water becomes bicarbonate, so it's a weak acid. So that's why that ultra pure water has a slightly acidic pH, because this unwanted weak acid gets in there. And you can view this as Lewis acid-base chemistry as well. This water molecule has pairs of electrons. It's the Lewis base. And it shoves those electrons into that carbon, which is acting as a Lewis acid. So Lewis acid-base definitions are useful if you don't have a proton involved. There's no proton involved here. If there's a proton involved, the Bronsted definition is much better. Yes?
Doesn't carbon also have 2 double pairs on it? Or would it only make double bonds?
The CO2, has 2 double bonds, each to an oxygen. The oxygens have lone pairs, but the carbon, as a result, is electron deficient. You can think about it this way. You think about the CO2 looking something like that. Well, that carbon has a partial positive charge, doesn't it? Has a partial positive charge because those oxygens are very electronegative. So again, when you think about a dipole that goes like that and like that. So that's why that thing is a good Lewis acid. It's a good Lewis acid because that carbon has partial positive charge. So again, we just go back to simple electrostatic arguments. You got this pair of electrons. Here it comes. Here comes this water molecule. Lewis base, Lewis acid. And so again, electrostatic arguments go a long way in helping you explain chemistry and physics. So that's another sort of Lewis acid-base reaction. And the other one where it's useful to think about Lewis is with metal ions. Oh, and by the way, we're going to talk about buffers next. A buffer is a solution that contains a weak acid and its conjugate base. So that solution now is buffered, and that's the same buffer that keeps your blood at pH 7.2. So this chemistry is also going on inside your body. It's the reason your blood has the pH that it does. I think that's right. Hold on, I got to think about that one more time. Let me think about that again. Scratch that statement. All righty. What else did I want to say? Lewis. Oh, yeah. Where's this? I don't know what happened to it. Is that it? Oh, that I don't want to lose. All right. So the final topic would be on Lewis acid-base chemistry would be, we can take our friend iron 3+. It can be viewed as a Lewis acid. So now, putting it all together, we see that if the atom is electron deficient, if it either has a lot of positive charge, as in iron 3+, or partial positive charge, as in this carbon, that's good clue that it might act as a Lewis acid. It wants electrons. It either is totally or partially positive charged. It wants electrons. That's what a Lewis acid is. So we can say that we can throw that into a solution containing cyanide, and you can make this very interesting molecule called Fe. Fe. Why? Ferric. High oxidation state. Iron 3+, high oxidation state, ferric. But what's happening, of course, is each of those cyanides is donating a pair of electrons. So the cyanide in this example is a great example of a Lewis base. And the iron 3+ is a Lewis acid. And so again, for me, thinking about Lewis acid-base chemistry, I start with the base. Because the base means whether you're talking about Bronsted or Lewis, it means you're talking about a molecule with a pair of electrons, whether it's a Bronsted definition or Lewis definition. Begin with the base. Now, to figure out if something is a Lewis acid, ask yourself the question, is it electron deficient? That's way electron deficient. It has 3+ charge. That's partially electron deficient because it has a partial positive charge. So this notion that molecules that have partial or total positive charge will make a good Lewis acid, that is a good way to think about this chemistry. Oh, let's quit. Hey, I got a show tonight. Who's coming to my show tonight? At the Atlantic. Beatles music. You'll be amazed. What?